Hi, everybody. Here we are back once again for another lecture of CHY 113 and today's deeper dive into the world of electrons. And so let's go ahead and just jump into our warm-up questions today, and we'll use those as a way to sort of recap all of the crazy information that we talked about last time. And so remember, the first thing that we looked at was looking at the different properties of a wave and using our wave equation in order to go back and forth between frequency and wavelength. And so in this question here, we have the wavelength of a wave at 5.63 times 10 to the negative fifth meters, and we need to calculate the frequency of that. And so, as per usual, I encourage you to pause the video now, try this question, and see what you can get. Hopefully you came up with 5.33 times 10 to the 12th hertz. And let's just take a look at that. And so remember that we're using our equation for waves, our light equation for waves. And so C equals wavelength times frequency, where C is equal to the speed of light, which is a universal constant at 3 times 10 to the 8th meters per second. That lambda equals the wavelength of our waves, and it must be in meters for these equations. And this Greek symbol nu stands for our frequency, which must be in hertz or cycles per second. And so in this question here, we are given a wavelength and we need to find frequency. And so I would rewrite our equation to be frequency equals C over wavelength. So that'll be 3 times 10 to the 8th meters per second divided by 5.63 times 10 to the negative fifth meters. And let's just double check and make sure that I did that right initially. So 3.00 times 10 to the 8th divided by 5.63 times 10 to the negative fifth. Sure enough, 5.33 times 10 to the 12th. And there we have it. Next, now we want to figure out what the color is of light that has a frequency of 5.77 times 10 to the 14th hertz. You have all the information you need right here to figure that out. So let's see what you can do. And let's look at how we went about this. So let me just write down our frequency first. It's 5.77 times 10 to the 14th hertz. And so we're going to use our same basic strategy. We'll use our light equation. Now, though, we have frequency and we want to solve for our wavelength. So wavelength will equal C over the frequency. It's 3 times 10 to the 8th meters per second over our frequency. And we plug this into the calculator. We get 5.19 times 10 to the negative 7th meters. Now, we're not done there, though. So this question is specifically asking us for what color the light is going to be. And so we have to remember that when we're looking at the electromagnetic spectrum here, so this is our entire electromagnetic spectrum, the wavelength of a wave will tell you what type of wave we have. And so longer wavelengths are radio waves. We start getting a little bit shorter to microwaves and so forth. And we have this very narrow band of roughly 380 nanometers up through about 720 or so. And that's visible light, the light that we actually see and interact with. Different wavelengths of light are what we then perceive as different colors. And so it's going to be easiest for us to convert this over to nanometers. And so we're going to multiply 5.19 times 10 to the negative 7th by 10 to the 9th. And that's our conversion to nano. Gets us to 520 nanometers. And so we look on our electromagnetic spectrum here, down in our visible spectrum that's blown up down here. And we see 520 at right here. And so a wave that has a frequency of 5.77 times 10 to the 14th hertz will have a wavelength of about 520 nanometers, and we would perceive that as a green color. From there, we moved on. We talked about a few other sort of obscure things concerning waves and probability a little bit, and the Bohr spectrum and the Bohr model of the atom. That led us into a discussion about quantum numbers, which helped to start to give us a lot of information about where an electron is actually located. And so the first quantum number we talked about was quantum number n, which describe our Bohr shells for us. And so in this question, we want to know how many electrons can fit on Bohr shell 3. So see what you can do. So the thing to remember there is that the maximum number of electrons that can appear on any Bohr shell is equal to 2n squared. And so 2 times 3 squared equals a total of 18 electrons on our third Bohr shell. This question is more about just having you go back and look at the different sublevels. And so write out the 4 different sublevels that can exist. That's our next level of organization after the Bohr shell, after n, is each Bohr shell is broken up into sublevels. And so write out each different sublevel and how many electrons can actually fit on each one. Hopefully this is what you got. The sublevels are S, P, D, and F, with 2 electrons maximum on the S sublevel, 6 electrons in a P sublevel, 10 electrons in a D sublevel, and 14 electrons in an F sublevel. And lastly, take a look here and determine which type of orbital is not possible. Hopefully you determine that 3F is not an orbital that can exist. And so what you have to remember here is that each sublevel or each Bohr shell splits into different sublevels. The first Bohr shell only has an S sublevel. So therefore we couldn't have, if we're talking about the Bohr shell 1, we would only be able to have a 1s possible. We wouldn't be able to have a 1p or a 1d, anything like that. Those sublevels do not exist in the first Bohr shell. The only sublevel that exists in the first Bohr shell is S. Our second Bohr shell splits into an S sublevel and a P sublevel. So I could have a 2s orbital, or I could have a 2p orbital, but I could not have a 2d or a 2f. Similarly, the third Bohr shell splits into an S sublevel, a P sublevel, and a D sublevel. And so it's possible for a 3s to exist, it's possible for a 3p to exist, it's possible for a 3d to exist. It is not possible for a 3f to exist. And the fourth Bohr shell splits into S, P, D, and F. And F realistically is as far as we go. When we get to the fifth sublevel, yes, it would be possible, or sorry, the fifth Bohr shell, it would be possible for the G sublevel to theoretically exist. And so you could have S, P, D, or G, or sorry, yeah, S, P, D, F, or G. But the reality is that we just don't end up having enough electrons to get there. And one of the things that we'll see and that we'll talk about today is once you start getting to that level of sublevel, so to speak, there are amounts of energy involved that we end up really not putting electrons there anyway. And so for sublevel purposes, we really only have the 4 S, P, D, and F. And that's our overview and our warm-up questions from what we talked about last time. And so today we're going to start getting a little bit deeper into some of this and start looking at how we'll use some of this to write out what we call electron configurations. But again, let's just go back and backtrack for what we talked about with electron arrangement. And so there's a level of arrangement to how electrons are organized around the nucleus. We start out by talking about the Bohr shells. And so what actual shell are we in, kind of like orbits around the sun. Those shells, though, are then broken down into sublevels. And we just talked about those, possible S, P, D, or F sublevels. From sublevels, we then get into orbitals. One orbital is a space where two electrons reside. And so, see if we write that out and again start breaking it down a little bit. So just like we just talked about, so Bohr shell 1 only has the S sublevel. And so there's one orbital in the S sublevel. Because remember, the S sublevel holds 2 electrons total. One orbital holds 2 electrons. And so the S sublevel consists of one orbital. And the first Bohr shell consists of just one orbital. The second Bohr shell splits into its S and its P. The S still only ever has one orbital, but the P sublevel now actually consists of 3 separate orbitals. The P sublevel holds 6 electrons total. Those 6 electrons are split up into the 3 different orbitals, and so forth. Our third Bohr shell split into its S sublevel with its 1 orbital, its P sublevel with its 3 orbitals, and its D sublevel, which is split into 5 orbitals. 10 electrons total in a D sublevel. Those 10 electrons are divided amongst 5 different orbitals. And then I'm going to run out of space once again, but Bohr shell 4, its S sublevel with its 1 orbital, its P sublevel with its 3 orbitals, its D sublevel with its 5 orbitals, and then finally its F sublevel with its 7 orbitals. 14 electrons can fit into an F sublevel. Those 14 electrons are split into 7 separate orbitals. And so we have here our N for our Bohr shells. So N equals 1, N equals 2, N equals 3, N equals 4, and so on. Our quantum number L, well, actually, we'll back up. I'll write that out up here. So N, we said, was our principal quantum number, defining our Bohr shell. L, we said, is the quantum number that is going to define our sublevels for us. If L equals 1, that's an S sublevel. Sorry, L equals 0 is an S sublevel. L equals 1 is a P sublevel. L equals 2 is a D sublevel. And L equals 3 is an F sublevel. And then quantum number M, sometimes you'll see it as M sub L, depending on what source you're looking at. That then describes our orbitals. We talked about M can equal values from negative L up through positive L. But realistically, what that gives us is information about how many orbitals can exist. And so, for instance, for L equal to 1, our P sublevel, L equal to 1 means that we could have possible M values of negative 1, 0, or positive 1. 1, 2, 3 possible values 1, 2, 3 p orbitals. So that's really how we use M. Let's try and decide if I wanted to go any further with that, but I think that sums it up. And so that's sort of the summary of a lot of what we talked about last time with quantum numbers. And this just sort of sums a lot of that up as well. We'll get a little bit more into spin a little bit later today as well. But the spin just means that the two electrons that are in an orbital spin in opposite directions. And we denote that by a +1/2 or a -1/2. Again, that number itself is meaningless. I'm not sure why somebody picked a half at some point. But it just means that the sign, positive versus negative, means that they are going to spin in opposite directions as they reside in that orbital. Sorry, just adjusting something off screen here a little bit so that I can see a better view. Sorry about that. Okay. And so that brings us now to looking at what we call electron configurations. Electron configurations give us a way to show precisely how the electrons are arranged outside the nucleus. They provide us a way with knowing, for instance, how many electrons are in what we would call a 1s orbital, or how many are in a 2s orbital, how many are in a 3p orbital, a 3s orbital, and so forth. And so when we are filling out an electron configuration, the first thing that we do, or what we're really looking at doing, is explaining or showing exactly how many of, we're looking at showing all the electrons in the atom. And we're looking at showing exactly where all those electrons are as far as what type of orbital they're in. And so let's take hydrogen just as our first very simple example. Hydrogen just has one electron. And so we want to define where that electron is. We have a couple of different overriding principles when we're looking at electron configurations. One of those is what we call the Aufbau Principle. Aufbau means to build up. There's an L in the word build, Professor Staples. And that just means that when we're doing these electron configurations, the way that I like to picture it is we picture the atom without having any electrons at all. Now we're going to put the electrons in there. We start by putting the electrons in there at the lowest energy level first. And we really envision these Bohr shells and our sublevels as energy levels. And so the Aufbau principle tells us that we're going to start in our lowest energy level first until that is full, and then we'll go to the next energy level and so forth, and we'll build up from there. And so hydrogen, with its one electron, is first going to go into Bohr shell 1. That just makes sense, closest to the nucleus. It's going to go there first. Within Bohr shell 1, the only type of sublevel that exists is an S sublevel. And so that's what comes next in our electron configurations, is what type of sublevel the electron is in. Hydrogen, atomic number 1, just one electron. And so that's what comes next, is saying how many electrons are in that sublevel. And we denote that with a superscript. And the way that we actually say this is 1s1. When we get later on, if we have a 2 in there, like for instance, helium has 2 electrons. So we're going to start with 1, going to go into the first Bohr shell into S, and then there are 2 electrons for helium. So we're going to have a 2 there. Same thing, we would say this as 1s2. We do not say squared. This is not a mathematical function. We're not performing any math operations with this. That 2 literally just tells us 2 electrons in the 1s orbital. And when we start getting more complicated than helium, we just start moving up from there. And so we use something like this as sort of our roadmap for the Aufbau principle, that our lowest energy levels get filled first, and then we move on from there. So let me leave this as big as I can. Okay, that'll work. And so we already looked at hydrogen and helium. Let's look at lithium. And so lithium, 3 electrons that we need to place. And so we're going to use the Aufbau principle. We're going to start with Bohr shell 1. Bohr shell 1 only has an s sublevel. We can fit 2 electrons max in the s sublevel. So we're going to put a 2 there. Now, Bohr shell 1 is completely full. The only sublevel that exists in Bohr shell 1 is the s sublevel. Once we fill that, and remember, 2 electrons maximum in the s sublevel. So once we fill that, then we're done with the first Bohr shell. We've filled this now. So next we're going to move to the second Bohr shell. The first sublevel that we come to in the second Bohr shell is the s sublevel, but we only have 1 electron left. And so we'll put a 1. So the electron configuration for lithium, 1s2, 2s1. Okay, then we move on to beryllium. Well, it's 4 electrons. Same idea. We're going to start first with our first Bohr shell, our s sublevel, 2 electrons there. We'll move on to our second Bohr shell, the s sublevel, 2 electrons there, and then we're done. Now we've placed in all the electrons for beryllium. After beryllium, what do we have? Aluminum? Nope, sorry, boron. With its 5 electrons. 1s2 fills up the first Bohr shell. Then we move on to the second Bohr shell to 2s. We can only fit 2 electrons there. We still have 1 more. So now we're going to move on to 2p. And we'll put 1 electron there. Let's move to something a little bit bigger. Let's move to, actually, let's do magnesium. 12 electrons in a neutral magnesium atom, atomic number 12. I know you can't see that when I point to it here, but I'm just pointing out that I'm looking at the atomic number, so you'll definitely want a periodic table in front of you as you're doing these. So atomic number 12. So let's go through our same process. First thing that we're going to fill is 1s. S fits 2 electrons, so we get 1s2. That's full now. Now we're going to move on to 2s. S fits 2 electrons, 2s2. Then we move on to 2p. P sublevels fit 6 electrons, so 2p6. Now we've filled up everything we can in the second Bohr shell, so now we're going to move on to 3s. And we have 2 more electrons there, so we get 3s2. Something funky starts to happen right here. You see this overlap, and I mentioned this last time, but we skipped over it. Now it's important for us because it turns out that the 4s sublevel will actually get electrons into it before the 3d sublevel. And so as you're going through this Aufbau principle, as you're filling these up, let's say that we are doing calcium, for instance. So calcium with its 20 electrons, we're going to go through our same process. We're going to start down here with 1s, fill 1s2, and then we'll go to 2s, 2s2, 2p6. We're going to move on to 3s, 3s2, 3p6. Now, before we go to 3d, we're going to go to 4s. And we have 2, 4, 10, 18. We only need 2 more. So we get 4s2. And that would be our configuration for calcium. So we fill 4s before 3d. And you see that pattern throughout the periodic table. You will always fill the s sublevel of the next Bohr shell before the d sublevel. So you'll fill 5s before 4d. 6s before 5d, and so forth. It gets even weirder with the f sublevels. And so let's look at a different type of pattern that we can use to help us figure this out. There we go. You can use a roadmap like this to help you remember the order of filling. You also have to remember how many electrons fit in each type of sublevel. Remember, 2 electrons fit in an S, 6 in a P, 10 in a D, and 14 in an F. But the way that you would use a roadmap like this is you would start right here. We're starting here at the beginning of this arrow. We're going to fill 1s. Then we come back around to fill 2s. Once that's full, we'll come back around and start in on this arrow and fill 2p and then 3s. And then 3p and 4s. And then, whoop, and then 3d and 4p and 5s, and so forth. 4d, 5p. Then you'll see that we actually fill 6s before we get to 4f. The reasons for that go beyond what we need to talk about in this course, but suffice to say that it's because even though a 4f is closer to the nucleus than a 6s, for instance, for the F sublevels start to get so complicated in energy and so high in energy that they're actually at a lower energy state, or sorry, a higher energy state than something like 6s. And so they get filled afterwards. Again, don't really worry about that. Just know that this is the order that that electrons will be filled in. And you just keep going until you've used up all the electrons we have. And so let's take a look maybe at one that's a little bit more complicated. Let's do iron. Iron's not that bad. And so iron, with its 26 electrons, we're just going to go through our roadmap here. We're going to start with 1s. So we'll get 1s2, fill that, then we come back around, 2s2. Now that's full. We'll come back around and do 2p. 6 electrons in our P, so 2p6. After that, we'll come down to 3s, 3s2. How many have we used so far? 2, 4, 10, 12, still 14 to go. So after 3s, we're going to come back around and get 3p, 3p6, then 4s2. Now we've used 2, 4, 10, 12, 18, 20. So we have 6 more electrons to go. And so after 4s, then we're going to come in and do 3d. D can fit 10, but we only have 6 more to go. So we're going to get 3d6. And there's our electron configuration for iron. Let's do one that's even a lot further down. Let's do tungsten. Tungsten looks like a fun one. 74 electrons. Symbol for tungsten is W. I know, go figure. But 74 electrons. We're just going to go through our pathway here. So we're going to start with 1s, 1s2, come around to 2s2, come around to 2p6, 3s2, then come around to 3p6, 4s2, then we'll come back around to 3d10, then 4p6, then 5s2, and then we're going to come to 4d finally, 4d10, 5p6, 6s2. Let's just track where we're at now. 2, 4, 10, 12, 18, 20, 30, 36, 38, 48, 56. I still have 18 electrons to go, don't I? So I've done 6s. Now I'm going to come around then and do 4f. Yeah, okay. Just counting them out to myself. So I'm going to do 4f. 14 electrons into 4f. I have 4 more to go. And so those 4 are going to now go into 5d. 4. Whew. Complicated, but you can follow the pathway. Just follow this path and you're going to get there. I will tell you, I'm not going to have you do much that involves Fs just because they're starting to get pretty big and unwieldy at that point. but you do need to know how to use this path. You're also going to do enough of these that this pathway, you're actually not going to need this big roadmap for that long, because you're going to do enough of these that you're just going to be able to rattle this off the top of your head. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and so forth. You're just going to be able to do that. But this is how we do electron configurations. Now, let's take a look at something real quick, though, because I'll be honest with you. When I'm doing a configuration now, I don't go through this whole pathway like this. If we take a look at the periodic table, one of the things that we see is that the end of the configuration can be predicted by where an element is in the periodic table. And this is now other terminology that we use for the table. We call our alkali metals and alkaline earth metals. These are the S block, because everything in here ends with S. In our first period, hydrogen and helium, these end with 1s. These end with 2s. These end with 3s and 4s. Everything here in the first row or the first column ends with 1s, ends with s1. And so hydrogen, 1s1. We have lithium right here, ends with 2s1. Sodium ends with 3s1. Potassium ends with 4s1. Right here, what do we have there? Strontium ends with 5s2, and so forth. We then have the P block over here. Everything in over here ends with P. Our second period here, these all end with 2p. These all end with 3p. These all end with 4p. And so if I want to know what the end is for, let's say, selenium, then selenium is 1, 2, 3, 4 columns down, or 4 rows down, sorry, in the periodic table. It's in the P block, so I know selenium is going to end with 4p, and it's 1, 2, 3, 4 elements over in the P block. So its configuration is going to end with 4p4, and so on. Our transition metals all end with D. And so you can count down, but just remember that we have that weird little overlap. And so everything in the first transition metal row will end with 3D. Everything here ends with 4D, and so forth. And so copper. Copper sits right here in the table. You know copper is going to end with 3D, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so this, using the periodic table like this, is a lot easier than just memorizing that filling order and memorizing the whole thing. And so what I do when I'm doing a configuration now is I, again, look at where an element sits. Let's say I want to do the configuration for, I don't know, maybe bromine. So bromine sits right here in the periodic table. So I know bromine is going to end with 1, 2, 3, 4 down. So its configuration is going to end with 4. It's in the P block, so it's going to end with 4p. And it's 1, 2, 3, 4, 5 elements over in the P block. So it's going to end, oops, sorry. Bromine is going to end with 4p5. And so I can just fill out my configuration up to there. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, ran out of space, 4p5. There's my configuration for bromine. Let's double check it. 2, 4, 10, 12, 18, 20. Ah, what did I forget? I messed up, didn't I? Nobody caught me on it. Maybe you did. It's because I ran out of space here. 3D10 goes in there. Let's make that a little bit bigger and easier to see. So again, let's backtrack there. I know bromine has to end with 4p5. So I'm going to fill up to that point. Let's just cross this mess out. I know it has to end with 4p5, so I'm going to build up to there. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, then 3d10, And then finally 4p5. 2, 4, 10, 12, 18, 20, 30, 35, and that's bromine. And so that's the way that I would fill out electron configurations. And so you could either just memorize the whole pathway, and you really will. Like I said, you're going to do enough of these. But then how you use the periodic table to help you figure it out, to help you see where the configuration is going to end. All right, sorry about that little glitch in the matrix there. I just had to go ahead and look at and see where I was going to be covering another topic and if I wanted to talk about it yet or not. I'll be talking about it later. So electron configurations provide us information about N and L for our quantum numbers. And so let's see what that means. And so if I'm looking at something, let's look at something a little bit easier like carbon with its 6 electrons, 1s2, 2s2, 2p2. So this tells us that for the 6 electrons in carbon, 2 of those are in the first Bohr shell in an s sublevel. And that's 2 of the electrons. 2 of the electrons are in the second Bohr shell in its s sublevel, and 2 of them are in the second Bohr shell in the p sublevel. And so, like we had mentioned, this is information about N, right here, quantum number N. And over here is information about quantum number L. And so that's what the electron configurations provide for us, is information about those 2 quantum numbers when we're looking at the electrons in an atom. Something called the box diagram now starts to give us further information about how the electrons might be divided into the various orbitals within the sublevel and what the spin might be of those electrons. And so when we're looking at box diagrams, we have to remember, and sometimes called orbital filling diagrams, which we'll look at in a minute. We have to remember the Aufbau Principle, which we've been talking about in relation to electron configurations. We also have to consider what we call Hund's rule. Hund's rule tells us that what we call degenerate orbitals are orbitals that have the same energy. And so, for instance, the 3 2p orbitals are what we would consider to be degenerate orbitals. They fill up separately before they start to pair up, and we'll see what that means in a minute. We also have what we call the Pauli exclusion principle, which tells us that individual orbitals which hold 2 electrons, those 2 electrons will have different spins. So let's take a look at what that means. And so Hund's rule tells us that, for instance, if we're looking at the configuration of maybe nitrogen, and I'm still in red, but that's all right, we're going to keep it. So nitrogen with its 7 electrons, we're going to be 1s2, 2s2, 2p3. And so what we're going to do with these orbital filling diagrams is we're going to now start showing these as the electrons in individual orbitals. And so here's our 1s orbital shown as a line. Here's our 2s. Now remember, and so there's 1 orbital in an s sublevel because each orbital holds 2 electrons. In the p sublevel, in the 2p, remember that we talked about there are 3 separate orbitals because the 2p sublevel holds 6 electrons total. Those 6 electrons are split between 3 different orbitals. And so now what we do in these orbital filling diagrams is we now depict electrons as arrows, individual electrons as arrows. Spin up, spin down. And so plus a half versus minus a half. And so we have our 2 electrons in our S, our 1s. depicted like this. So there's our 2 electrons spinning in opposite directions. And that gets us to the Pauli exclusion principle as well. 2s, now we filled up 2s. Now we have our 3 electrons to fill in for nitrogen, or to fill in, sorry, for our 2p sublevel. Hund's rule tells us that these electrons do not arrange themselves like this. This is incorrect. What Hund's rule tells us is that the way these 3 electrons are going to arrange themselves is they're going to fill in individually within this sublevel. And that's the key part, is that these are going to fill up individually within the sublevel first. So we still always look to fill a sublevel before we move on. That's what the Aufbau principle tells us, that we're going to fill 1s before we go to 2s. We're going to fill 2s before we go to 2p. But Hund's rule tells us that as we're filling 2p, now we're going to put 1 in each individually before we ever pair them up. Then we would come back around and fill if we need to. And so if we moved on to oxygen, for instance, with its 8 electrons, one s2, 2s2, 2p4. Now we're going to have 1s, 2s, then 2p1, 2, 3. Now we can fill in and double up, spin in opposite directions. That's Hund's rule. And the Pauli exclusion principle telling us that electrons are going to fit, or electrons are going to spin in opposite directions. By convention, if there's only 1, we usually write that as up. And then when we pair, we write the second one down. So here's the example that we just looked at with nitrogen. So same thing that we just did. And we've already talked about all this. And just here's a few examples. So here's lithium, 1s2, 2s1. Here's our configuration. Here's our orbital filling diagram. Beryllium, 1s2, 2s2. So here's our orbital filling for beryllium. Boron, 1s2, 2s2, 2p1. Carbon, 1s2, 2s2, 2p2. Note how we are following Hund's rule. 2 electrons in 2p are in separate orbitals. Nitrogen, which we've already looked at. Oxygen, which we've looked at. Fluorine, 1s2, 2s2, 2p5. And then neon. Now we've completely filled up the second shell. And so here we have an example of aluminum. And so aluminum, 1s2, 2s2, 2p6, 3s2, 3p1. So here's our orbital filling, our orbital box. These are 1s2, 2s2, 2p6, 3s2, and 3p1. And this is the same thing, but sometimes you'll find an orbital filling diagram that sort of fills things vertically like this to show the corresponding energies of things. Noble gas notation. We can shortcut configurations and box diagrams. So let's take a look actually at the configurations of, how do I want to do this? We'll start with neon. And so the configuration of neon, 10 electrons, 1s2, 2s2, 2p6. Configuration of sodium with its 11 electrons, 1s2, 2s2, 2p6, 3s1. Magnesium with its 12 electrons, 1s2, 2s2, 2p6, 3s2. Oh, where do we go to after magnesium? Aluminum. 13 electrons, 1s2, 2s2, 2p6, 3s2, 3p1. Then silicone, then I'll stop there. 1s2, 2s2, 2p6, 3s2, 3p2. What is it that these all have in common? Take a look, see if you can figure it out. These all have in common this 1s2, 2s2, 2p6. Those are, and that's the configuration of neon. So what we can do is instead of writing 1s2, 2s2, 2p6, we can actually write neon in brackets, and that stands for writing out that whole configuration. That stands for writing out this. That gives us a shortcut notation that we can use in order to just more easily write some of these longer configurations. And so we can write aluminum, for instance. We can write aluminum by doing this, by writing neon, 3s2, 3p1. Sorry about that. I hate that that little screen pops up. There we go. And so the way that we would do a noble gas notation is we look to see where an element is in the periodic table. And then what we can do is go to the noble gas that comes before that element. So for instance, iron. Iron's right here in the periodic table. So if we go back and look at the noble gas that comes before iron, it's argon. And so we can write argon in brackets. And then after argon, we would do 4s2, the rest of the configuration, then 3d, 1, 2, 3, 4, 5, 6 to get to iron. So that would be our noble gas shortcut for argon, or sorry, for iron. We could do one of the largest elements in the periodic table, radium. So 88 electrons. I could do the noble gas shortcut for radium by going to the noble gas that appears before it, which is radon. We get radon right there. And then after radon, I would just have 7s2. And so in some questions, depending, looking at your homework and tests and so forth, there will be some times that I allow you to use the noble gas shortcut. There'll be other times that I want you to write out the whole darn thing, just to make sure that you're getting practice rattling off the whole entire configuration. But this noble gas shortcut does give us a handy way to just look at the outermost electrons, which we'll see really come into play for us down the line. And I know you can't see this, and I don't even know why I still have it up there. So we'll just skip over that real quick. Actually, we already talked about transition metals. Let's skip through some of this. Okay. An electron configuration of ions. All you do there is just adjust your electrons as necessary. And so for instance, if I'm looking at the electron configuration for oxygen 2-, oxygen would normally have its 8 electrons, but O2- has 10 electrons. And so you would adjust your numbers in your electron configuration accordingly. For cations, it does get a little bit different. So it turns out that for cations, you're going to remove electrons from the orbital with the highest quantum number, the highest principal quantum number. For most things, that's for a lot of elements, that's pretty straightforward. For magnesium, in order to go to magnesium 2+, we're going to remove these 2 3s electrons. And so here would be our configuration for magnesium 2+. For transition metals, it does get a little bit different. And so for iron, if we want to go to iron 2+, we need to remove 2 electrons. For transition metals, we're going to remove those 2 electrons from the orbital with the highest principal quantum number. which means we're not going to take them from 3D here. We're going to take away these 2 electrons in 4s. I don't know why that's skipping around like that. There we go. That was weird. And so we end up with a configuration that looks like this for iron 2+. It's those 4s electrons that will be removed because they're in the higher principal quantum number. And so we do have to remember that when we're looking at the electron configuration of transition metal ions in particular. Okay, we're going to actually call it good there on this lecture. I was going to get into the periodic trends, but I'll actually do that in another quick lecture and keep those separate. And so that is all for today. Electron configurations and orbital filling diagrams, starting to really look in detail at where electrons are located around the nucleus. And so I hope you have enjoyed learning about electrons as much as I've enjoyed teaching you about it. Digest this. It's a lot to think about. Go back and look through the textbook. Watch some Khan Academy videos, watch some other resources, and really try to piece this together and really try to picture what's going on. But that is it for today. Do some practice problems, work with us a little bit, and I hope everybody has a great day.